Last time we studied about how to analyze CMOS circuit by considering transistor as switch. For this kind of transistor, if you want to turn it on, you must apply 0 volt or logic low, at gate terminal, and then this transistor will turn on. That means this point and this point will short together, like a switch, namely this one, this point drain, right? Then terminal, and this one will be source, right? And this is gate terminal, something like this, gate, like a switch. When you apply 0 volt or logic low signal at gate terminal, this switch will close or turn on. We will link or connect between drain and source terminal, which make this point and this point become the same voltage potential or short together. Then the current can flow now from drain to source. Similarly, for this transistor, this one is active high, no inversion bubble. This transistor will turn on when apply 5 volt or high voltage at gate terminal. When you apply this one, it will link between this point and this point, between drain and source, short together. That's all. And from this one is basic configuration connection of inverter. Namely, this PMOS or active low transistor will connect to plus 5 volt or VDD. And for this active high transistor, connect to ground. And we use this point as the output. This output will have opposite logic to input. Namely, if you apply 0, the output will be 1. If you apply 1, output will be 0. And we also analyze the NOR function and NAND function. For NOR function, when you analyze last time, we did it by apply 0, 0 and consider each transistor turn on or off. For example, if you apply 0, 0, right, and then this one is active low, so Q2 turn on. Q4 also active low. When you apply 0, Q4 then turn on. That means this point and this point is short together. And for this one is active high transistor. That means when you apply 0, 0, so these two transistors are off or open circuit. Then by the result, this output is connecting to VDD. So then output is 1 or high. And if you apply, for example, 0, 1, this one turn on, this point and this point short together. like a switch, right? Like you push switch, then connect between this point and this point. And this one active flow, so this one open circuit or off. And 0 here, this one active high, but you apply low, so this one off. And this one high, active high, and you apply high, so this one turn on, then short between drain and source terminal. By the result, this output now connect to ground, so output become 0. So you analyze by this method. Okay, you can analyze by this method. Okay, by apply all possible value input to A and B. Okay, for 2 input, so you have 4 possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. And this one also you can analyze. Okay, but please note something about the circuit configuration. The first thing that you already know last time, for active flow switch, you connect to VDD, and active high, it will connect to ground side. Okay, for all the circuit. The second one, if you note, if the upper part of the circuit Q2, Q4 with control by A and B respectively, this transistor and this transistor connect in series, and Q1, Q3 are also controlled by A and B, but the connection between this transistor and this transistor connect in parallel. And this one series, this one and this one parallel. Series mean when you connect it, if the current flow, it will be the same current. And for parallel, okay, this point, and this point have the same potential. This side also, this point and this point, okay, same voltage potential. So it's parallel. And about this circuit, if the upper part connect in parallel, the lower part will connect in series. For this type of circuit connection, actually you can analyze the circuit by consider only upper part or only lower part. For example, let I ask you when this output will be 1. Namely, this output will be 1. The output terminal must have some part connect to VDD, right? So that means both Q2 and Q4 must be on. That means A must be 0, right? Active flow. B also must be 0, okay, to make Z to be 1. So Z will be 1 when, okay, or if and only if A is 0 and B is 0. Based on this condition, actually you can write the expression as A prime, right? A is 0, right? And B prime. So your equation for this logic gate function is Z equal to A prime and B prime. Okay, or you can analyze just only the lower part of the circuit. Okay, how? Okay. Now let me change the equation. When this output will be 0 or connect to ground, right? this output will be 0 when what? When Q1 or Q3 turn on, right? If Q1 turn on, there's path that connect to ground with this path, or when Q3 turn on, this path connect output to ground. So you can write the statement Z will be 0 when, okay, when or if and only if Q1 on, that means A must be 1, right? Or what? Or B, right? B must be 1. That means when you write in the expression, okay, is A or B, right? If A is 1, B is 1, A or B will be 1 or 1, right? Which equal to 1. But you want the output, okay, become 0 based on this condition that A is 1 or B is 1. But if you just write A plus B or A or B, the result will be 1, right? Not 0, okay? So you must invert this expression, namely the output Z equal to A or B, and then invert out of this the same result. Namely, if you consider the upper part of the circuit, your result will be Z equal to A prime and B prime. If you consider the lower part of the circuit, your result will be Z equal to A or B, and then invert out of this. Okay, actually this one and this one are the same function. A plus B prime equal to A prime and B prime. Keep it based on some switching algebra or Boolean algebra. Actually, in high school, you see something like this. Not P or Q. Maybe your high school maybe use this one. Not P or Q equal to not P and not Q. Okay, same thing. Actually, this one is De Morgan theorem. De Morgan. So, if you use this method to analyze, you will obtain the function certainly and fast, okay, faster and easily to get the result in mathematical function. So let's try to use this method to analyze the circuit. Okay, so if you analyze the upper part of the circuit, Q2, Q4 connect in parallel, right? That means output Z will connect to VDD, or output Z will be 1 if and only if what? This one turn on or this one turn on. That means A is 0 or B is 0, right? So A is 0 or B is 0. So you can write the expression as A prime plus B prime. Okay, then finish. Okay, this is the function of this circuit. Or you also can analyze the low part of the circuit. When you consider low part of the circuit, you must ask the question when the output will be 0. So the output will be 0 when Q1 turn on and Q3 turn on. That means A must be 1 and B must be 1. So if and only if A is 1 and B is 1, So A and B. Okay, but this expression is for z equal to 0, right? Your result will be 1. So your final expression for the function is inverse of A and B. That's all. And again, okay, based on De Morgan theorem, A and B, inverse of A and B equal to A inverse plus B inverse. So about this circuit, this one. Oh, this one, if you analyze by substitute all possible value of the input, you must substitute 16, right? 0, 0, 0, 0 until 1, 1, 1, 1. 16, okay, combination of the input. And each one you must consider, oh, this one turn on or this one off, one on, off, right? It takes time. Anyway, if you take the configuration of the circuit connection, you will see that, for example, this one controlled by A, right? Okay, controlled by A. This transistor controlled by B, right? And this one controlled by C, and this transistor controlled by D. Okay, consider from this, right? And this one controlled by C, this controlled by D, this one controlled by B, and this one controlled by A. Okay, please note that A, okay, for Q2, Q4, which is controlled by A and B respectively. At the upper part, these Q2, Q4 connect in parallel. In the lower part, the transistor that controlled by A and B connect in series, right? Parallel, series. And for C and D, okay, the transistor that controlled by C and D at the upper part connect in parallel, but at the lower part connect in series. And this group of transistors connect to this group of transistors in series. But at the lower part, this group of transistors and this group of transistors connect in parallel. So actually this kind of connection is called duality. Duality together. Duality. Namely, if the upper part connect in parallel, the lower part will connect in series. If the upper part connect in series, the lower part must be parallel. Okay, something like this. So, if the configuration is something like this, you can analyze just only upper part of the circuit or lower part of the circuit. Okay. So, if I consider upper part of the circuit, that means I consider when the output will be 1. That means there is some path, right, that connect to plus VDD. So let's consider, let me write the control signal near the gate terminal of the transistor A, B, C, D. So the output will be 1 when A parallel to B, right? And C parallel to D. So you can write as A or B, right? Parallel together. And this set D, C or D. And these two groups or these two sets connect in series. So you add these two terms together. Then you get the function of this circuit. Then finish. Okay, very fast. Okay, easier and faster than this method. you can analyze the low part of the circuit. Oh, sorry, this one was active flow. Sorry, active flow. A must be 0, right? Or B must be 0. C must be 0. D must be 0. Okay, don't forget. Okay, it's active flow. Okay, and the low part of the circuit is active high. This one controlled by A. This one is B, right? This one is C, D. Okay, A, B in series. A, B in series. So A and B, C, D series together. C and D, and this set and this set connect in parallel. That means you must all these two terms together. Based on this expression, when A, B, C, D is 1, 1, 1, 1, your result will be 1. But based on this condition, okay, it will make the path connect output to ground, namely output becomes 0. But this expression is 1, so you must invert out of this, okay, to complete the function. Namely, the output Z equal to invert of what? A and B plus C and D. That's all. And based on this one, output Z equal to invert of A and B plus C and D. So if you write the circuit diagram, A and B use this AND gate, C and D use this one, and this term or this term. Okay, you bring the output of these two AND gate all together and then invert. So you invert. So this kind of configuration then is called AND or invert. AND or invert. Okay. AND or invert configuration. Similarly, for this one, at the upper part of the circuit, the transistor controlled by A and B connect in series. Okay, the lower part of the circuit, the transistor controlled by A and B. Okay, connect parallel together. And for CD, okay, controlled by CD, connect in series. The lower part of the circuit, CD parallel together, and this set parallel together, this set series together. So you can analyze just only consider upper part of the circuit or just only the lower part of the circuit. Okay, let's consider upper part of the circuit. Okay, don't forget it's active flow, right? So the output will be 1 when C is 0 and C is 0, or A is 0 and B is 0. So you can write the expression for this function as A and B or C and D. That's all. Okay, easy, right? Okay. What about when you invert. Don't forget invert. Okay, because it's active flow. Okay. Namely, this transistor will be on when A is 0. Then A is 0, right? Then A is 0, A prime, and B prime, right? B is 0, B prime. Then it's become 1. This term also. And if you consider the lower part of the circuit, then you consider when the output becomes 0. Namely, this part, this one or this one must be turned on, and this one and this one must be turned on. Okay, so when C is 1 or D is 1, right? C or D, right? Is 1. A, B, okay, A or B is 1. and because this and this connect in series, so you add this one. And don't forget, this condition can make the output become 0, so you must invert out of this, okay, to complete the function. Namely, if you apply A, B, C, D with 1, 1, 1, 1, okay, and to make the result Z become 1, you must invert all of this expression. And when you write out the circuit diagram, okay, A or B, this one, C or D, this one, and okay, and two term, okay, bring the output of our gate and together, and then invert, okay, invert. So this configuration is set all and invert, all and invert. Okay, it is some basic structure that you should know. Okay, and this some note, okay, for the circuit analysis, okay, and also the circuit design about the connection for the PMOS network, okay, and NMOS network. For PMOS network, we will pull up, namely we connect to VDD, and NMOS network is pulled out, namely connect to ground, like this, connect to ground, okay, this part connect to VDD. And if the upper part of the circuit connect in series, the lower part of the circuit must connect in parallel. Okay, if we use some graph to represent the switch or transistor that controlled by A, this one, okay, this line, or this edge, represent switch or transistor. We will use transistor as switch, right? That controlled by A, and because of active load, so we like bar to show that this one is active load. For transistor Q4 also, right? We turn on when B is 0, and Q1, Q3, okay, this transistor and this transistor parallel together, okay, controlled by A and controlled by B respectively. And your output is this point, Z. Okay, that's all. Okay, for this one also, this one controlled by A, controlled by B, parallel together, active low A, active low B, and this one controlled by A, active high, this one controlled by B, active high. So you write series together, and your output is this point, okay, output Z. Okay, and how about this one? For this one parallel together, this transistor parallel together, controlled by active low, right? Active low controlled by A, B, and this one CD, right? CD. And for this one controlled by C, controlled by D, connect in series. Okay, this one, and this one controlled by B, this one controlled by A. Okay? Connect in series, and this part and this part, okay, parallel together. This one and this one, okay, parallel together. And the output of the circuit, output Z, is this point. Okay, and this one also, okay, similarly. If the upper part of the circuit connect in series, okay, the lower part of the circuit that controlled by the same signal, just active low and active high, but same input, must duality together. Namely, if the upper part of the circuit connect in series, lower part must be in parallel. Okay, if the upper part of the circuit parallel, the lower part of the circuit must connect in series. So then you can analyze just only upper part of the circuit or lower part of the circuit, okay, to find out the output of the function. One thing you must be careful just about active low. Active flow. So don't forget invert for each input parameter. And if you consider the low part of the circuit, for the low part of the circuit, each input is active high signal. But you don't forget that if this one turn on, you make the output become 0, right? So your function, don't forget to invert out, okay, all of this, okay, to make the output become 1. Okay, to the design. So if you want to design the circuit, actually you can design it very easy. For example, if I start by 2 switch, active low and active high, A bar B. If I add B parallel to A, this part, low part must series. If I add C parallel series to B, low part of circuit C must be parallel to C. C, B must be parallel together. And if I add D parallel to D, I must add D series to B in the low part. And if I add E series to D at the upper part of the circuit, the low part of the circuit, E must be connected in parallel to D. Okay, must duality together. And then when you finish, you just connect between this point and this point together, which will be output Z. And this one connect to VDD, like 5 volt. And this point connect to ground. Okay, that's all. And then you just replace, okay, the each edge or each line by transistor that controlled by A, B, C, D, E. Okay. A, B, C, D, E. Okay. That's all. The part of the circuit also. You can draw the circuit diagram by applying the transistor symbol for A, B, C, D, E. Okay, follow this connection, that series or parallel. That's all. Okay. Very easy. And someone, if you have equation, first of all, if you have equation and you want to write out the circuit, it's very easy. For example, if you have this kind of expression, okay, you can write something like this: A DE, right? DE in parallel, B and DE, so B must series, right? And or C, okay, C parallel this part, and A this one. When you obtain this one, so if you want to draw the upper part of the circuit, you can do by find out the duality connection. Namely, you just consider this method. Okay, you just add node in each method. So and this one, when you link between this node and this node, link edge, okay, edge between this node and this node, it cut, it pass through this line that controlled by E. That means this edge must controlled by E also, but this one active high, so this one must be active low. Again, connect between this point and this point and cut D line, so this one must controlled by D but active low. And this one also, this point, okay, this one cut B, right? Then this line controlled by B. What else? This to this cut the line controlled by C, so this one must controlled by C bar. And what else? Okay, pass through this line that controlled by A. So this one controlled by A bar. And okay, you just draw the line to connect all nodes together. And what else? Oh, okay, this point and this point. This point and this point. Okay, we go to infinite. Go to infinite. Go to infinite. So when you separate, then you obtain, okay, the duality circuit. After that, you just connect this one and this one together like this. And don't forget that your output is the point or the junction between the upper part and lower part of the circuit. Okay, like this. So now you can complete the circuit design. Okay, very easy. Okay, now let's continue to the next page about the logic level. Actually, you already know for logic high and logic low. Okay, but itself it's not just only 5 volt for logic high or not only 0 volt for logic low. Actually, there is sampling, right? Sampling for the standard for CMOS standard. Okay. For logic high, is covered from 70% of VCC, okay, to 100% of VCC. For example, if your VCC is 5 volt, so the minimum value that should be logic high is 0.7 multiply 5, then it becomes 3.5 volt. So 3.5 volt to 5 volt is logic high, and for logic low is 0 to 30%. Namely, we use 5 volt, so it's 0 to 1.5 volt, and undefined or abnormal between this length. Okay. Anyway, if you consider the output of logic gate, for example, this one, and maybe to use to some logic gate, you know that, okay, the signal at each point in its circuit, for example, must be logic high. The minimum value must be 3.5 volt, right? Okay. If this output, the output from this logic gate is 3.5, what happened? Okay. If this signal, okay, is used through many logic gate, what happened? Some voltage drop may be occur. So if it drop, it then become lower than 3.5, right? For example, maybe 3.0 or 2.8, for example. So that means the signal level now is lower than logic high. So some operation may be not so good. That means to avoid this one, some standard for the output level of logic gate, we will have some margin. Namely, for CMOS, right? The standard is the minimum output for logic high. Minimum output level for logic high is VCC minus 0.1. Namely, for VCC 5 volt, the level is 4.9. Okay. Namely, the minimum value of logic gate, okay, must more than 4.9 volt. So even some loss occur when it feeds to another input of another logic gate. It may be dropped to, for example, from 4 0.9, maybe up to 4.8 or 3.9. So it still be okay, right? Because it's still in the length of logic high. For logic low also. So for this zero, the standard is the highest, right? The highest, okay, maximum. It's ground plus 0.14. Okay, around this point. At the output. Okay, there's some margin, okay, between internal signal in the circuit and the output, okay, to prevent some voltage drop or some noise. Okay, next parameter you should know is fan out. Fan out means what? Okay, for example, maybe this. Okay, this circuit maybe okay. Let's consider this one. If I connect this output to some logic gate, so what happened? It may be some current occur. For example, if I apply 1, right, this one turn on, this one turn on. For ideal case, okay, the resistance is 0 ohm, right? 0 ohm, right? For each transistor when it's on. But in practical, it's not 0 ohm, right? Maybe 10 ohm or 100 ohm, okay, something like this. So what happened if the current flow, for example, in this direction? If the current is 1 milliamp, for example, that mean the voltage across this one is what? Is 10 millivolt, right? 10 millivolt. Okay. So what happened if there are many logic gates connect to this output? For example, if there are 3 logic gates and each logic gate, okay, take a current around what? 1 milliamp, for example, 1 milliamp. If there are, for example, 10 input, okay, use the signal from this transistor, from this logic gate. So that means the total current at here, if there are 10, right, is 10 milliamp. That means the current flow to this one, right? So the voltage across this transistor, if internal resistance is 10 ohm, that means the voltage across this one is 100 or 100 millivolt or 0.14, right? And this one also 0.14. That means now this output not 0.4, right? It's 0.24. Okay. If I increase number of logic gate that use the signal from this output, that means, okay, the current flow to this one become higher and higher. So this voltage then become higher also. Then it's possible to be higher than 0.3 volt or become 0.5, also possible. That means what happened? That means the voltage level now, it may be in some abnormal, right? For example, if it's over than 0.3 volt, maybe it be in abnormal or undefined, okay, logic value. So that means you cannot connect, okay, the output to many input of logic gate. The maximum input of another logic gate that can use from the same output. That's still key. Okay, the logic level collected. Okay, it's called fan out. Okay, fan out. For example, if the maximum input current for each logic gate is 1 milliamp, and the output maximum that can keep the logic level is 0.2 milliamp. That means this one can connect to the maximum logic gate to what? 0.02 milliamp, namely it's 20, right? Microamp. And each one is take 1 microamp. That means the maximum number of logic gate that can use the signal from this output is 20, right? 20. So this 20 is final. And another parameter is transition time. In ideal case, the signal in the digital circuit, it can change from low to high suddenly. Namely, it can change 0 volt to 5 volt suddenly. But in practical, because some internal capacitance or some internal resistance, okay, it make the behavior of the circuit like RC circuit. Namely, if your input change, something like this, your output may be change in exponential curve. For example, like this, from this one to this one, okay, and something like exponential occur. So it takes time, okay, and the time that it takes is called transit time. To measure transit time, normally we don't measure at the beginning 0% to 100% of the steady state. Okay. To make it easy to measure, we measure it start from 10% to 90%. Okay, the time that obtained from this 10 to 90% is called rise time. And for fall time, okay, it's measured when it's changed from 90% to 10%. Okay, so it's transition time. And for propagation delay means if you have some kind of circuit or logic gate, if your input change, okay, you must wait a little bit before the output change. It's like this input, okay, come into the logic gate or circuit, and it take time, right? It take time. The time that it take, okay, after input change until the output change, is called propagation delay. So, for example, when input change at here, and the output, something like inverter, right? When input change from low to high, your output must change from high to low. Okay, the time that it take before see the result at the output after input change is called propagation delay. Okay, for this one, output change from high to low, so like propagation delay. And for this one, okay, input change at this point, right? And the output change after this change of the input with this propagation delay. Okay, change from low to high. And if we consider transition time also, we can write something like this and this one. Okay. And okay, for this circuit, note there is no connection to VCC at the drain terminal. Then what happens if I apply 1 Okay, this one turn on, so output Z connect to ground. Then it become logic 0, right? And what happens if I connect apply 0, 0 to A and B? So this one off, right? How about the output? Output not connect to ground, but it's also not connect to VCC, right? That means now this output become open circuit. Okay. So to use this one, normally we must add pulled up transistor. Namely, it's connect this transistor will link between this output to VCC. Okay, this is what is called pulled up resistor. Pulled up resistor. Okay, after you add pull up resistor, so what happens if you, for example, if you apply 0, 0, this one turn off, this one turn off. Okay, how about the output? If this output still be not connected to another logic gate, that means there is no current, right? That there is no current in the circuit. That means voltage across this resistance is 0 volt. That means this point and this point will have the same voltage potential. If this point is 5 volt, so this point also 5 volt also. Now it's not open circuit, right? But half, okay? But half voltage level for logic high. So after you add pulled up resistor, the result will be high, 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 and then low for the input 0, 0, 0, 1, 1, 0, and 1, 1 respectively. Okay, for this one, okay, it's called open drain CMOS logic gate. In this case, it's 2-input NAND gate, and we use this symbol to show that this one is open drain. For TTL family, and the similar one is called open collector. Okay, you just know the name. If you see this one, okay, it's the same thing, similar thing. Okay, for this one, for example, if you connect this resistor to LED, okay, and want the current from supply, okay, by through LED. If this current not over that amount of current that each transistor can stand, okay. So if I want to calculate, for example, want to calculate the value of resistor that's suitable to make LED turn on. If the current that's suitable for LED is on is around 10 milliamp. So and when LED turn on, voltage across LED may be around 1.6 or 1.8 or 2.4. Actually, it's based on the color, that this LED is red LED or green LED or blue LED. So different voltage across LED when it's on, also different. For this example, if when LED is turned on, and the voltage across LED is 1.6 volt, and if this transistor turn on and is on, the voltage across this one, or the output value is 0.37 volt, and because supply is 5 volts, so that means now from this to this point is 0.37 volt. For the across LED is 1.6 volt. That means the potential at this point is what? It is 1.6 and 0.37, then it become this point, then it become 1.97, and this point is 54, this point is 1.97. So the different voltage, okay, across this resistor then is 5 minus 1.97. So now if you know the amount of current that you want to use, first one is 10 milliamp. So you just divide voltage across R and divided by current, okay, pass through the resistor. Okay, it's the same because it's series, right? Same current pass through LED, okay? 10 milliamp. So okay, when you do the calculation, your result may be 303 ohm. But in practical, you cannot find out this value. Okay, exactly the near value. For example, 270 ohm or 300 ohm or 330 ohm. It's okay because the current may be not the current that you use. Okay, maybe not 10 milliamp, maybe 10.5 or 9.8 milliamp. It still be also okay because the light from LED, okay, it's not so different. Okay, and the application for this open drain logic gate. For example, if you connect this output and this output and this output together, what happened? And this R pull up. This point will be 0 if, okay, this transistor, this set of transistor, or this set of transistor, or this set of transistor, okay, turn on. Output, this output will be 0 suddenly. So, and when the output will be 1, all of this must be turned off. Okay, all of this must generate logic 1, 1, 1 at here. This output then become 1. So the function is like AND, right? AND function, but there is no AND gate. It has only this junction. So then it's called wide AND function. Okay? AND function just only connect, okay, the wire together from open drain, okay, from open drain logic gate. Note that you can do this actually this kind of open drain logic gate or open drain output. You cannot do this for the general logic gate because, for example, if you connect the output directly, so what happened? If this one, if I apply some value at here and make the output become 5 volt, and this one maybe make this one turn on of 0 volt. So what happened? Connect directly together, and the wire have very low resistance, right, near 0, and the voltage different just a little bit. It make, okay, it produce large current, okay, pass through the transistor. So the transistor may broken, okay, may burn, may be broken by this high current. So do not connect output together, okay, for the normal logic gate. Okay, and for this one it's called 3-state buffer. Actually, it can be buffer or inverter also possible, but they want to show you some example of buffer that have enable control input. Okay, enable. If enable is 1, this buffer, okay, we will operate normally. Namely, if A is 0, output will be 0. If A is 1, output will be 1. Okay, normal operating of this logic gate if enable is 1. But if enable is 0, this output will be not connect to input A. We will not connect to the output of this logic gate. You can treat it as open circuit or high impedance. So, okay, how does it work? Okay, for detail, okay, let's analyze. When enable is 0, when enable is 0, 0 at here, 1 at here, right? 0 and anything is 0, and then input then become 1 at here. 1 or anything become 1, when input then it becomes 0 at here. So this one active flow but apply 1, so this one is turned off or open circuit. 0 but this one active high, so it's turned off. So this output then now not connect to VCC, not connect to ground. So it's become open circuit or high impedance. High impedance means resistance. Okay, similar meaning like open circuit. For open circuit have very high resistance or high impedance. Okay, and what happened when enable is 1? When enable is 1, 1 input then becomes 0, 0 or input A, then it's A and then input then A prime at here, and for this one 1 and A and then input, so it becomes A prime at here. Okay, now if A is 0, what happened? A prime is 1, right? A prime is 1, so this one turn on, make the output become 0. Oh, the same as A, right? When enable is 1, output of this buffer will be same as value of A. And if A is 1, okay, the output will be 1 also. Okay, if enable is 1. Okay, that's all. Okay, very easy. And the last component that you should know is transmission gate. There are two, okay, complement CMOS, okay, and the enable control signal, this one and this one must be not the same, must be different. Namely, if enable is high, this active flow enable must be 0. So this one turn on, then this one turn on. That means now output B connect to input A. Very easy. And the kind of the example, this one. Okay. At first, let's consider this one first. If enable is 1, active flow enable is 1, is 0, okay, opposite. That means this one turn on, this transistor turn on, then B now connect to A, okay, when enable is 1. And if enable is 0, this one opposite, then become 1, then turn off. Now B is not connect to A, separate together, or you can treat it as open circuit at the output. Okay. Yeah, let's try to analyze this one. This one, okay, if you note this set of CMOS, the side connect to VCC correctly, and this this one connect to VCC directly, right? And this one connect to ground directly. So this part act as inverter or NOT gate. Namely, If S is 0 at here, 0 at here, so this point will be 1 at here. Okay, input 0, then 0 at here, 0 at here. Okay, and now what happened? This one I keep high, right? So this one is on. 0 at here, then this one is on. How about this one? 1, but I keep low, so off at here, off at here also. That means now output connect to X. Namely, when S is 0, okay, the output Z will be the same as input X. Similarly, if S is 1, what happened? When S is 1, this output will be 0, right? 1 at here, 1 at here. So this one turn on, this one turn on, this one off, this one off. So output Z then now connect to Y. So actually this one is some kind of multiplexer or mux. Okay, this one, okay, you have selector signal S to select that which input, okay, can go to the output. Okay, just select. Okay. By the result of the circuit analysis, when S is 0, output Z will be the same as input X. And when S is 1, okay, your output will be connected to Y. Okay. Okay, that's all for this chapter.